This is a cutaway view of a DC motor. As you can see, they're much more complex than the simple squirrel cage induction motor that we've used before. The rotating part is called the armature, and it has the commutator. The commutator is copper segments that act as a high-speed switch. They are contacted by the brushes, and the brushes are connected to the supply out in the real world. That is how the energy is brought to the armature through the brushes to the commutator. The commutator is actually connected to the armature coils, and this allows current to flow through the armature coils, and the armature will create a magnetic field. The field coils, or field pieces, are housed in what's called a frame. They are housed, the field coils are the shunt field and the series field. This is the rotating part of a DC motor. It's called the armature. It consists of a shaft, a commutator, which is broken up into very small segments that are contacted by the brushes. The brushes get the current from the outside, from the supply, and make the connections to the coils in the armature. The armature is wound with several coils, and they create a magnetic field for the armature. Okay, so let's discuss motors. They convert electrical energy into mechanical energy, but at the same time, they are actually generators. DC motors are actually generators. As they begin to rotate, they actually generate CEMF, which is counter EMF. The faster they rotate, the greater this counter EMF becomes, and this counter EMF actually opposes the flow of current through the armature. Hopefully you noticed with the video from Peter Vree that starting and stopping of the motor can be accomplished by opening and closing the armature circuit. However, with armatures, they actually have very low resistance, 1 ohm to 1/100th of an ohm. So therefore, their inrush currents are actually very large, different than AC motors, which are 5 to 7 times full load current. Inrush currents on a DC motor can go way more than that. Current reduces, though, in the motor because of the increase of the counter EMF. Okay, we're just going to take a motor as an example. Motor having a rated voltage of 250 volts DC, has an armature resistance of 1 ohm. And however, what we're going to look at is that under a partial load, now it's just got a little bit of a load, not full load, it's going to run with a current of 10 amps. So let's do a calculation of the proximate CEMF, counter EMF. Okay, if we have an armature resistance of 1 ohm, however, under this running current we're going to show is at 10 amps. By Ohm's law, the effective voltage, the voltage that will cause 10 amps to flow through 1 ohm, E is equal to I times R. We do that by Ohm's law. So that's 10 times 1, which comes out to 10 volts. However, the counter EMF is the difference between that effective voltage and applied voltage. So if we take applied voltage minus the effective voltage, we actually come up with the value for counter EMF, which is 240 volts. Here's the motor wired up, ready to go. M contacts are the contacts from the motor starter. As soon as the M contacts close, current flows through the armature, and immediately we have 250 amps flowing through the armature. It reduces as counter EMF increases. Okay, from the video from Peter Vree, seeing that if the armature circuit is open, the motor will come to a stop. However, if the shunt field is open, we actually create a bomb. So actually an open shunt field is dangerous. The motor can run away, it'll increase in speed up to the point where the armature can rip apart. Sparks at the brushes actually can turn into an arc flash. So how can this be prevented? As with motor control, we've done before in ACs, control is accomplished by use of relays. What we have here is a coil of a relay placed in parallel with the shunt field, monitoring actually the voltage across the shunt field. If a fault occurs here at the red X, that coil will de-energize and we can use it to shut the motor off. However, if a fault occurs here at the red X, there will still be voltage across the shunt field. It'll continue to run, but our shunt is open, causing this bomb to occur. So let's look at this type of protection again. A coil in parallel with the shunt winding, it can detect an open that occurs between the supply and the field, but if an open occurs in the shunt winding itself, it can't detect this. The voltage will still appear across that shunt winding and the relay will be energized, and as far as it knows, there's nothing wrong. Here's actually a better configuration for protection against loss of the shunt field. We use a current operated relay. The coil of the current operated relay is in series with the shunt field. If for any reason we lose current through the shunt field, the system can be configured to de-energize the motor, opening the M contacts, and the motor will come to a stop. Okay, so let's look at this, the way it's set up. The field loss relay, the coil for the field loss relay is in series with the shunt field winding. It is actually a current operated relay. That means that it requires that current that's flowing through that shunt field in order for it to become energized. If an open circuit does occur in the shunt field circuit, this relay will de-energize. Here's the contact of the field loss relay, FL. It's actually in series in the motor control, so that when it opens up, when it de-energizes and opens up due to loss of shunt field current, it will actually shut off the motor contactor, bringing the armature to a stop. Okay, now let's look at starting current of a DC motor. Different than AC motors, which are 5 to 7 times full load current. DC motors can be much, much higher. So we have our example motor of a rated voltage of 250 volts and an armature resistance of 1 ohm. The starting current by Ohm's law will be around 250 amps. So how can we reduce this? Current can be reduced by putting a resistor in series with the armature and thus reducing the current. Here we're going to show you that we're going to use an example of a 5 ohm resistor. The total resistance is the armature resistance plus this accelerator resistor that we're going to put in series with it. Makes a grand total of 1 plus 5 is 6. So now what we look at the starting current, I is equal to E over R. 250 volts over a total resistance of 6 ohms gives us 41.67 amps starting current. Here we have our 5 ohm resistor, our accelerating resistor in series with our armature. So notice that when the M contacts pick up, the inrush current is reduced now to 42 amps approximately, and that reduces as the counter EMF builds due to the increased rotation of the armature. Having a look at that again, once the M contacts close, current flows through the resistor and the armature, maximum of 42 amps, and as the armature accelerates, speeds up, the counter EMF increases and the current decreases. The resistance is good for reducing the inrush current, but it is undesirable to have that resistor in the circuit permanently. The resistor will actually hinder the flow of current through the armature, and therefore the armature won't be able to produce as much torque as it really should. The best solution to this is to bypass the resistor once the armature has built up enough counter EMF. And the best way of doing that is to put a timed contact in parallel. Here we have that contact in parallel with the resistor. It's labeled as 1A, A standing for acceleration. When the M contacts close, current flows through the resistor, and therefore we have a reduced inrush current. But once the counter EMF is built up, so we won't have that huge amount of current, the 1A contact closes and the current is bypassed around the resistor. Here we have the start-stop control for our DC motor, very similar to what we use for the AC motor. But in this case, when the motor contactor is energized, it also picks up an auxiliary contact that closes and starts the timer relay, which is 1A, the acceleration relay. Here we've got it labeled out for a time delay of 2 seconds, and after that 2 seconds, what would happen is the contact 1A will close and short out or jumper out across the resistor.